Hello, friends, and welcome to a little quick lesson here on concentration time graphs when we're dealing with an equilibrium system. So what we're going to be doing is we're going to be taking a look at the idea of the Chatelier's principle, but we're going to view it graphically on our concentration time graph to see what's happening when we impose changes to our equilibrium system. We want to be able to see how does that system respond in reference to that original change. And if you think about the Chatelier's principle, we know that any change that we make to an equilibrium system, the system itself should respond to oppose the change, right? So I need you to always remember that when we're talking Chatelier's principle and looking at the impact, we want to remember that it's always going to oppose the change. So if we increase the concentration of something, it should oppose it by trying to decrease it. If we increase the temperature, the reaction is going to respond by trying to lower the temperature somehow, right? And we'll get into all of that in some of our examples here. So we're going to be working with this reaction H2 gas plus I2 gas is in equilibrium with 2HI, the delta H value of positive 26.5 kilojoules per mole. And I just want to illustrate first how this reaction can be shown reaching the same sort of position on our concentration time graph, no matter whether we start with our reactants or products. So I'm just going to bust out the pen here. And we'll start with forward reaction. So if we were to consider our H2 and our I2, and we want to look at our reaction, and I'm going to just sort of label my axis here. So this is concentration. We'll say it's in moles per liter, and my time, let's say seconds, whatever it is. It doesn't really matter to us. And let's just say that for all intents and purposes, right here, we've got 1 molar, 0.5 molar, and so on up here, 1.5, and way up near the top, we'd have 2, right? So I'm going to do that same scale here so that we have it on both. And then we'll get to looking at how this changes. So if we think about our reaction, let's say we put in H2 and our I2 to start with. And let's say we have an initial concentration of 1 mole per liter. So we're starting out right here. When we are looking at this particular reaction, then, as the reaction proceeds, we're eventually going to reach some equilibrium. And so as the reaction goes in the forward direction, it's going to produce HI. But at some point, that HI production is going to sort of maintain a consistent level. We'll end up with a consistent amount of HI, and that's the point when we reach that equilibrium. So on a concentration time graph, it might look something like this. As we're going along in time, we're using up reactants, and our reactant concentrations will get smaller and smaller until it levels off and it stays at a constant point, let's say 0.5 moles, just to make it easy, right? Now, at that same time, when we look at this, we're going to see that the HI concentration would be starting at 0, but based on the ratio of 1 to 2, we know that as this reaction is proceeding, it's going to increase and eventually, again, level off. And where it levels off, right, when these concentrations have leveled off, and their slopes essentially now become 0, we've reached that point of equilibrium where we have that specific amount of product that's not changing concentration, because remember, at equilibrium, our forward reaction rate should be equaling our reverse reaction rate. So if we consider this equilibrium, so let's consider it an equilibrium instead of one directional arrow. If we're going in the forward direction, this is what we would see. Now, if we were to think, okay, let's start instead with the reverse. What if we started with HI? Let's start with 2 moles of HI. So I start with an entire container full of HI. And over time, that HI is going to react, and it's going to get used up until we get that point again where it levels off. In the creation of our H2 and our I2, we'd be starting with no H2 or I2 at the beginning, but as time goes by, we're slowly generating that HI to the point where we then level off. And again, that point in both of these scenarios where I'll just put in a black dotted line. At this point, this is where we reach equilibrium. okay, because our concentrations aren't changing. They're staying constant at this point. Same right in here, right? That's where we reach our equilibrium. So this is an example where I can reach the same equilibrium whether I start with reactants or products. It doesn't matter. Okay, I'll end up at the same equilibrium. So let's say we've got this reaction of that we've been looking at, this reaction involving H2I2 and HI. And let's consider this reaction, but look at what doing some changes to the equilibrium can be. So we'll go back to having our same sort of scenario here. Our reaction, I'll just write it off to the top here, was H2 plus I2 in equilibrium with HI. And everything was gases. I can write that in too if we want. And this delta H was positive 26 kilojoules per mole. All right, so there's our reaction. And if we think about what's going on, I just want to make sure I can get this fit onto the page here one time. We're going to take a look again at that same equilibrium. So imagine we've reached that same equilibrium position that we are. So we're just going to start from this point. So imagine we've done this initially. We've reached an equilibrium. And so we're sitting at equilibrium where we have some HI up here. I'll do it in blue, I guess, this time. And I'll do maybe purple as my H2. And my I2, I will do red. Okay. So my I2 are sitting down here. That's where my I2 and my H2 are at equilibrium when we start out. And this, remember, was concentration, moles per liter. And this was my time, let's just say in seconds. So now we're going to apply our understanding of the Chatelier's principle. We're going to take this equilibrium. We've reached equilibrium. So here's our equilibrium concentrations when we're at equilibrium. And right now I'm not worried about the numbers, but we want to look at how these changes, what they're going to do, what they're going to visually look like on this graph. So if we take a look at increasing H2, immediately when we make that change of increasing H2, we should see, I'm going to do it in purple for the H2, we should see basically a rise in H2. So its concentration should go up, and it's going up relatively quickly because our change is pretty much instantaneous. Boom, we inject a bunch of extra H2, so the concentration goes up. So we do that really fast. It's basically going to be that vertical line showing the H2 go up. Now, if we think about this equilibrium, we've just caused the H2 to go up. So our system wants to respond by doing the opposite. It wants to oppose the change. So it's going to try to make the H2 go down. So over time, the reaction is going to slowly proceed, and we're going to create more product. We're going to use up some of that H2 until we eventually flatten out again the concentration, meaning we've reached equilibrium. So our reaction is going to try and use up that H2. That's what it's going to do. If we, the experimenter, put in more H2, the reaction is going to try and use it up. So you'll see something like this. Now, typically in a change like this, it's not going to decrease by like some crazy new amount, like drop significantly. It's going to use up some of it, but it's not going to get back to the same equilibrium position. We're not going to get back to the exact same amount of H2 anymore. At the same time this is happening, though, we have to consider what's happening to the other reactant. If the reaction is shifting towards the products, right? So here our reaction, I'm going to just write in here, shifts to products. If our reaction is shifting to products, that means our other reactant in response should go down, right? So we should see that I2, there's no initial change, but we should also see it slowly going down until it flattens out. Because our reaction is taking H2, it's taking I2, and it's going to be making HI. So lastly, we should see that HI increase in concentration, right? So we should see the HI go up, and then it'll flatten out as well. And where we've got that scenario of all flattening out, maybe I'll do a little black color there or some gray. When it all flattens out again, so let's say right in here, it's not the best straight line, but it'll work. That's where we've got a new equilibrium right here, right? So that's what would happen with our change. We would see that shift, we would see that initial change in the hydrogen, and then the response by the system to try and lower that hydrogen's concentration, use up some of that extra hydrogen, and to use it up, we got to use up some I2 as well. Okay, and then that's going to generate more HI. Let's look at the next scenario here. The next scenario, I believe, was what if we decrease the HI concentration? So what if, and this happens a lot actually in industry, is where we will go and we'll take, as product is being made, we'll pull it out of the container. So we can decrease the HI concentration. So we lower it. The response by the system then is to try and fight that and bring it back up, right? So what we should see is we should see an initial drop. Okay, let's say we take out that much. And then the response by the system is to make more. And it's a slower change, right? So we see a curve to it. And then it flattens out again, right? So this second response, we're going to see this reaction. We lose HI, the system wants to make more of it. So we know here that the reaction has to shift to the products again, right? It's trying to make more HI. So we see that change. Okay. Now to make more HI, that means H2 and I2 are getting used up. So we should see their concentrations drop. So I2 is going to go down. Now again, there's no initial change to these. We just see the drop and then it flatten out. And the H2, same thing. We should see that initial change, slow drop, and then flatten out, right? And where we've achieved equilibrium again, we see now another new equilibrium position, right? So here's our next equilibrium position gets achieved right in here, right? So that's a new equilibrium position again. Okay, so every time a change is made, we've made two changes so far. Our first one happened here, and then our second one happened here, right? So every time we make that change, we should see something occurring. Our system is going to have to respond to try and oppose it, and we should be able to see that in our concentration time graph. So let's look at the third change. The third change is a change in temperature. So if we increase temperature, right, we raise it, the response by the system should be to try and lower the temperature. So if it's going to try and lower the temperature, that means it needs to get rid of kinetic energy. So if we think about where energy is in this reaction, positive delta H tells me endothermic. Yeah, if you said endothermic, that's right. So we should have energy over here, right? So we know energy plus the H2 plus the I2 is what's making the HI. So if we increase the temperature, just imagine that as adding a bunch, right? A temperature increase is like adding a bunch of extra energy to the reaction, right? Which is going to cause it to want to get rid of that extra kinetic energy. So it's going to shift to the products again. Okay, so our reaction here is going to shift to the products to try and use up that extra energy. So if it's shifting to products, it's making products. That means we're going to see in this one again, we're going to see our HI go up slowly and then level off. You'll see with temperature that there's no initial increase in concentration, right? Nothing initially was increased concentration-wise. All that was changed was energy. So we don't see any initial change. We just see the response, that slower response by the system, right? So we're seeing that shift to products. It's making product, making that HI. Remember, we're doing HI in blue. And that means if we're shifting to product, reactants are getting used up. So we're going to see again, we're going to see I2 getting used up. So it's going to slowly drop over time and then level off. And the H2, same thing. We should see it slowly drop over time and then level off, right? To achieve a new equilibrium position. So right in here, right? Keep following that down where we've got everything leveled off. That's our new equilibrium has been established there, right? And the position is different than it was previously. So every time we're making this change, we see some response by the system, where possible, to oppose the change. Okay. Our last sort of set of things to consider would be what happens when we decrease pressure or change a volume, right? If you remember Le Chatelier's principle, decreasing pressure, this is something the system can deal with. Okay, so a lot of time in a lab, we might set up a reaction in a constant sized vessel, but that vessel, we as the experimenter might have the ability to adjust its pressure right inside. So that can be done by changing the volume of the container for us. So sometimes they have like a piston that you can push down and then lock in place to change the pressures, or raise up and then lock in place. So we're going to try and examine, when we examine pressure and volume, we're going to consider that change. If we change the volume, we're really looking at the impact of pressure, because we're going to look at the reaction is not able to change the volume of the container that we're doing it in. Okay, when you're in the lab working, you're working in like solid glassware. It's not changing the size of that glass. So let's look at like what it will do to pressure. So if we decrease the pressure, the system response would be to try and raise the pressure, right? That's the ultimate goal is for this one will be to try and raise pressure. So I'm just going to write this down here. It's going to try and raise pressure, right? To do the opposite, raise the pressure. That's what the reaction wants to do. So to raise the pressure, remember, to raise pressure, we need more gas molecules slamming into the side of the container, right? So we need to look at this in the fact that the reaction is going to shift to the side of the reaction that has more gas molecules, because if there's more gas molecules, there's more gas molecules to smash into the side of the container, hence raising the pressure. So ideally it wants to shift to side with more gas. That ideally would be what the response would be. So if we look at our fourth change happening, we decrease the pressure, the system response is try and raise it, it wants to shift to the side with more gas. So if we look at our reaction, we've got H2 gas, we've got a molecule of I2 gas, so we've got 2 moles of gas on the reactant side, we have 2 moles of gas on the product side. So this is a scenario where this reaction can't do anything in response to that. Okay. All we're going to see happen is, because of our initial pressure change, we'll consider pressure with our volume, right? If we raise the pressure, that means that the volume has, if we decrease the pressure, that means that the volume has obviously increased. So we might see on our concentration time graph, if we do that, where we raise the pressure, because remember, pressure and volume are inversely related. Okay. If we raise the pressure, the volume's gone down. That's how typically we do it. So what you might see in that case is an initial concentration change, because as soon as we change the volume, remember that C equals N over V. So if we're changing V, right, when we change this, that's going to impact the concentration, right? So if the volume goes down, okay, because of an increase in pressure, if the volume goes down, we're going to see a change in our concentration, where our concentration should go up, right? So an increase in pressure is going to cause concentration of gases to go up. A decrease in pressure should mean that the volume has increased, so we know that the concentration of gases should go down. So when we look at this, kind of gotten off topic, but when we look at this anyway, what you'll see is that because of this change of volume and pressure relation, that we might see initial changes to concentration right off the hop for any gases. Okay, so if we decrease the pressure by increasing the volume, that's going to cause all concentrations to drop. So if I have my concentration going down, right, initially all my concentrations drop. So I'm going to see that go down. I'm going to see my 2 go down, and I'm going to see my H2 go down initially, right? So we've got that initial drop happening. Then the system responds to the pressure change. So if we decrease the pressure, the system tries to raise the pressure, shifting to the side with more gas. But in this case, it can't respond. So all you would see is that at these new concentrations, just a nice flat line. Okay. Because it can't respond, because there's 2 moles of gas on each side of the reaction. And I need red. Okay. So unfortunately, in this case, the system couldn't respond to the change. Our other change here was a decrease in volume. So again, decrease in volume, think about that, a decrease in volume as being an increase in pressure. So the system will try to lower pressure in response, because the system's not going to, we're going to be working with rigid containers, the system's not going to change the volume of the container. So if we have decreased the volume of the container, the system can't go and up the size of the container it's in. It's just going to have to deal with the pressure change. So decreasing the volume means we increase the pressure, so the system tries to lower the pressure, which means shifting to the side with less gas. All right, so if it tries to shift to the side with less gas, in this case, we don't see that happen because both sides have the same amount of gas. But remember, we got to go back to this initial thing. If the pressure changes because of volume, there's going to be a concentration change as well. So when we decrease the volume, that's going to cause all concentrations to rise. So what we will see with this is an increase by whatever amount, okay, in our concentrations initially. So we'll see our I2 go up, and we'll see the H2 go up. Okay, a bit more. So we see that because of that change in volume, right? The decreasing the volume causes the concentration to go up. So we see all those initially, and then the response by the system to try and lower the pressure, shifting to side with less gas. But in this equilibrium, we can't do that. There's 2 moles of gas here and 2 moles of gas there. So it can't respond. So then we just see it again, flat line in this case. And the other color is blue. So let me see this flat line again. It can't respond in this particular scenario. Okay, so that was our decreased volume. The last scenario we had was adding a catalyst. Remember that adding a catalyst causes the rate of reaction to increase. All adding a catalyst will do would be to change how quickly we reach equilibrium. If we are already at equilibrium, adding a catalyst doesn't do anything for us. Okay, so since we're already at an equilibrium, right, the concentrations are staying constant over time. Forward and reverse reactions are happening at the same rate. Adding a catalyst is going to influence those the same way. So if it's going to increase the forward reaction, it increases the reverse reaction, and we're going to see the exact same equilibrium position. Adding a catalyst isn't going to change that. So for this one, we would see, again, just a flat line. Just adding a catalyst is not going to influence our system at equilibrium. Okay. What we will see if we put a catalyst in at the very beginning or along with doing one of these other changes, when the system response occurs, so let's say you were to look back at this first scenario where we increased H2, the system response, if we'd added a catalyst and increased H2 at the same time, all that would mean is that the system response would happen faster. So instead of taking however many seconds it took to get to this new equilibrium position, maybe it does it in half the time, right? But because we're already at an equilibrium position and all we did was add a catalyst, it's not going to change where that equilibrium position would be. Okay. So that's how we can see some of these changes on a concentration time graph. So good luck playing with the Chatelier's principle and working with concentration time graphs. And don't be afraid to ask questions if you need anything. Okay.